The theory of everything has been found. Hello, my name is Harris Samantopoulos, and I have found the theory of everything. This is part 2 of the theory of everything. If you haven't seen part 1, I urge you to see that first. In part 2, we will see what my theory tells us about special and general relativity. Did Einstein get it right? And I will tell you about the connection model. This model not only tells us how the fundamental forces of the universe are connected, but it also tells us what protons and neutrons are made of. But first, my theory speaks of a physical field at a fundamental level. It would seem that this would represent an absolute reference frame. However, the field cannot be used as a reference frame. To understand why, we first must understand time in relation to the field. Before special relativity, there was a belief in absolute time and space, where these two things would be seen as a preferred reference frame, as though there was time ticking away in the background and a preferred location. A physical field would seem to represent a preferred frame, but the field cannot be used in this way, and the reason for this is the difference between the undistorted field and an object in the field that by its very nature distorts the field. Let's imagine the field with no objects in it. It would be in an unchanging state because the energy in the field is neutral and there is nothing in the field to change it. So its state would be constant, therefore it would have zero time. For time to exist, a state must change. Objects in the field change that part of the field they occupy, and they are always in motion. An object is made from quantiparticles and from field lines that are distorted inward. So now that part of the field that is the object is independent from the rest of the undistorted field. Objects possess energy, and the field does not have relative energy. So objects have time because they change, and time can be measured between them. However, it's not possible to measure between objects with time and something with zero time, like the field. Absolute space is something that never changes, something that is at absolute rest. With this definition, we would have to say that absolute space defines the field. Therefore, can the field be used as an absolute position? This would mean placing an object at absolute rest with the field. Is this possible? Hypothetically, yes, but very unlikely, and only for a short time. If an object was at absolute rest, we would not know about it. The problem with detecting an object at absolute rest is that the principle of relativity would still apply, because we could be the ones at rest, or we could be the ones in motion. The laws of physics would still apply for that object at absolute rest. Therefore, the field does not offer an absolute space. An object at rest is in the same state as an object in uniform motion. So you could be at rest, or you could be moving. Of course, nothing is at rest. Everything in the universe is moving. We just use the term at rest to simplify things. So this is the principle of relativity. However, our strict application of this in all situations leads us into paradoxes that physicists can't solve. They think they can, but they have no idea. However, there is a solution. Let's imagine there are only two ships in the entire universe and no other reference points. The ships are moving at constant speed, passing each other. Each ship can claim to be at rest or claim to be moving. However, not only would each ship not know if they are at rest or moving, they would not know which direction they are moving in. It would be valid to say that they are moving in the same direction and one is just moving faster, therefore passing the other one, as it would be to say that they are passing each other moving in opposite directions. It would also be true that each ship can claim that the other one is undergoing time dilation, and they are not, because each ship claims to be at rest, and measuring each other's time dilation would come to the same result. The principle of relativity is valid with the example of the two ships, but applying this in all circumstances brings us to a meaningless state. It doesn't resolve anything, and we can't advance our understanding of the universe. But once we understand what really causes time dilation, the paradoxes disappear. I explained before in part 1 how an object accelerating through the field has its shape changed. It becomes narrower in front because it's impacted by an increase of oncoming quantum particles. The result of this is that the front contracts in size. This is length contraction. So this theory can give us a physical reason as to why length contracts. The consequence of this contraction is that the field lines are pulled more onto the object, increasing the energy around it. So now we have an object with more energy around it. This slows all functions for the object because it has to move through more energy. Therefore, time moves slower. The higher the velocity, the greater the energy, and the slower time moves. We know that a moving object has more energy than it does at rest. As we have seen in part 1, the section momentum, acceleration will increase energy around an object. So time and energy are inverse. The faster you go, the slower your time. This mechanism for time dilation explains how the muon can get to the Earth's surface before it decays. If you recall in part 1, my description of an unstable particle, which is a particle with mass too large to be contained by the field lines, then this would include the muon. The high velocity of the muon contracts the field around it, creating more energy surrounding it. This slows the decay. So an outside observer would see the muon decay slower. But what does the muon see? The muon will see outside events moving faster than its time. So acceleration gives more energy to an object, and that will change the passage of time for it. But if we don't know about the acceleration of an object moving past you, then all you can say is that either one can be at rest or moving. If we measure its time dilation, it will be the same as if we measured your time dilation. But now that we understand what really causes time dilation, is there a way in which we can say that in relation to two objects, which object's time is going slower? The same frame is one in which two objects share the same velocity, because they would have, relative to their mass, the same energy. Two objects can be separated by a considerable distance, or be moving past each other, away from each other, towards each other, or in any direction, but as long as their velocities are the same and constant, then their time will be the same, and they will be in the same frame. Separate frames of reference are any two objects moving with different velocities. To simplify things, we can refer to one as being at rest. When we have two objects next to each other and therefore moving at the same speed, then we have two objects in the same frame. If one object accelerates, then there are now two different frames, and we can distinguish between the two frames because the energy around the accelerating object has changed. But there's something else we need to know about the consequences of moving through the field. All matter, from photons, spaceships, planets and galaxies, move in a wave-like motion. And the reason for this is that our universe is not just one field, but three coexisting fields. So each field exists within each other field. The first field has its lines at 90 degrees to each other. The other two fields have their lines orientated at 45 degrees to the first field. So an object moving through the field is forced by the 45-degree lines to move up or down or side to side, thus moving in a wave motion. So it will have a wavelength. Now, there are two consequences of this. One is that over a set distance, your wave motion will cause you to travel a longer distance within a set distance. And the faster you travel, the less distance you cover over time, because your wavelength becomes shorter. Let's break it down this way. We will say for the moment that time dilation does not exist, and then we will include it. So without time dilation, you are going to travel a distance A to B. You use this equation, T equals D divided by V, to find out how much time it will take to get to B. When you see that the time is up, you stop. However, you have not arrived at B. This is because your wave motion causes you to cover a greater distance within the set distance. So in the set time, you have not arrived. This would mean that T equals D divided by V is not true, but we know it is true. If we now include time dilation, your time will be moving slower, allowing you to cover the greater distance created by the wave motion. Therefore, T equals D divided by V will be correct. Time will move slower to correlate with the greater distance the wave motion creates. Your time moving slower and your wave motion are inexorably linked. So what we see is that time and distance share the same dimension. It's not just time dilation, it's also distance dilation. What we also see is that T equals D divided by V is only true for the person in the moving frame. If there was someone waiting at B waiting for you to arrive, they would have to wait longer than T equals D divided by V. In special relativity, T equals D divided by V is true for the moving frame and rest frame. How they get around this is by saying that the space between A and B is contracted by the moving object. So if A and B were planets, they would be pulled together by a very large distance. No one can ever explain how this is possible. My theory does tell us that the two planets would be pulled closer together. However, that distance would only be by the contracted length of the moving object, and that would be a very short distance. Both twins, Adam and Ben, are on Earth next to each other. Therefore, they are in the same frame. Adam is the one that accelerates away. So now there are two different frames because, due to Adam's acceleration, he has more energy around him, therefore slowing his time. Adam's time will be moving slower all the way to the return point. When he gets to the return point, his speed slows. When he slows, the energy around him progressively lowers. Therefore, the rate of time quickens. So at the return point, the rate of movement for his time is equal to Ben's rate of movement for time. At that point, they are in the same frame, but only for a short time because he quickly turns and accelerates back to the other twin. When he accelerates back up to speed, once again his time is moving slower than Ben's. As I said before, acceleration increases energy around an object, slowing its time. Before Adam left, they calculated the return journey would take 10 years at 80% of the speed of light, using T equals D divided by V. But 10 years later in Ben's time, who is the waiting twin at rest, Adam has not returned. This is due to the increase in distance the wave motion produces. It will take Adam another 6.6 years to arrive, a total of 16.6 years in the rest frame of Ben, who is waiting. So Adam, the travelling twin, will be 10 years older because T equals D divided by V is only true in Adam's moving frame, and Ben, who had to wait longer, is now 16.6 years older. So the waiting twin is 6.6 years older. It is not valid to say that Adam, the travelling twin, is at rest and the Earth is moving. That is only valid with the two ships scenario. Adam is the one that has accelerated. This creates more energy around him and therefore slows his time. The Earth has not accelerated. As I said before, the contraction in distance is only the length contraction of the object travelling. So Ben needs to use t times gamma to know how long it will take for Adam to arrive. Let's now say that Adam's speed is higher at 99% the speed of light. When we do this calculation, we find that it will take Adam 57 years in Ben's time to get back, a much longer time. But why is this so if Adam is moving faster? The reason for this is that the faster your speed, the less linear distance you cover, because your wavelength is shorter. There are many attempts to explain the twin paradox using gravitational acceleration, or a change in direction, or some silly space-time diagram. Acceleration has been dismissed as a way of solving the paradox. However, they are not privy to the real reason for time dilation, that acceleration increases energy around an object. They try to use scenarios where there is no acceleration, but that only brings us back to the two ships and no other reference frame scenario, where every frame is at rest. We should also realize that the twin on Earth at rest is subjected to gravitational time dilation. If that gravity is stronger than the acceleration of the moving twin, then the at-rest twin will be younger. The speed of light is constant in all frames of reference and through any medium it can travel through, but it will take longer to traverse a set distance depending on the frame or the medium it's in. Mediums like glass and water distort the field. This distortion shortens wavelengths. Therefore, it takes longer for light to pass through these mediums. A moving object is contracted in size, contracting the field around it, so the field lines are closer together. Therefore, light must travel a longer distance in association with the contracted object. Let's imagine a very long spaceship moving at high speed, and someone ahead of it sends a light beam towards the ship. Before it gets to the ship, the beam is moving through undistorted field. Once it enters the ship, it must travel a longer distance due to the distorted field created by the contraction of the ship's length. The speed of light stays constant. However, because it's taking longer to traverse the length contracted ship, it correlates with the dilated time on the ship. An observer in the ship, due to time dilation, will measure light to be moving at the speed of light. Once that light has left that frame, its wavelength is no longer shortened. It then travels to the outside observer without any distortion. When entering the outside observer's frame, it conforms to the distortion of the field around that observer. So that observer will also measure light to be the speed of light according to that frame of reference. An outside observer will be excluded from being able to measure the reduction of progress of light over distance that is happening in the ship. If an observer at rest was to measure a beam of light coming out of a moving ship from point A to point B, they would measure the speed of light to be correct. They must take into account the longer time it takes for light to pass through the ship. So they must add onto that time the speed of the ship. Now, I need to be clear about what I'm saying. You cannot add your speed to the speed of light so that the speed of light is faster than 300 million meters per second. However, in the moving frame, because it takes light longer to traverse a distance, the observer at rest needs to add the ship's speed to it. So, to both observers, the speed of light is 300 million meters per second. That's the end of part 2. In part 3, I'll talk about the connection model. This model connects all the fundamental forces and a lot more. I will introduce a new constant that in fact is not new, because Einstein used this in general relativity, but he didn't know what he had found.